Hello again from the Phoenix Science Operations Center at the University of Arizona in Tucson. I'm Sarah Hammond, the Public Affairs Manager for the mission. Now, we know it's been a few weeks since we've been with you live to give you an update, but in that period of time, our scientists and engineering teams have been very, very busy as Mars continues to delight and surprise us. And we've been looking up, and we've been looking down, and we've been looking around, and we're going to tell you a little bit about what we've been finding. So please let me introduce our panel for today. Joining us from Washington at NASA headquarters is Michael Meyer, the Chief Scientist for the Mars Exploration Program. Peter Smith, Principal Investigator for the Phoenix mission from the University of Arizona. Bill Boynton, Co-Investigator and Lead Scientist for the Thermal and Evolved Gas Analyzer, also known as TIGA, from the University of Arizona. Victoria Hipkin, Mission Scientist for the Meteorological Station from the Canadian Space Agency near Montreal, Quebec. And Mark Lemon, Co-Investigator and Lead Scientist for the Surface Stereo Imager from Texas A&M University. And we're going to start our panel today with Michael Meyer.
Thank you, Sarah. From 200 million miles away on the bleak, frozen surface of the Martian Arctic, Phoenix lander has been toiling away for 65 sols, and for its effort, it has tasted success. The mission is going very well, and it's been proving very successful, and Mars has certainly proved itself to be interesting. Mechanically, the spacecraft is operating great, and there's plenty of power margin to carry us beyond the waning summer. So with that, what we'd like to do is announce that we're going to extend the mission to go to the end of the fiscal year, which brings it to like Sol 124. And as a demonstration of how well the mission has been going, the mission has already met the minimum mission success, and we're pretty close to completing full mission success. The orbital resources of Mars Odyssey and the Mars Reconnaissance Orbiter have been doing a great job with synergistic measurements that have not only helped us in terms of telecommunication relays, but in the science itself. They've been able to take local measurements from Phoenix and expand them to the region. And also, the orbital assets, by looking down, and with Phoenix looking up, we've been able to make measurements simultaneously of the same column of the atmosphere. So Phoenix is studying the hydrological cycle and the polar processes, looking at the recent history of the subsurface ice, and then also potentially habitat in the soil-ice interface. And with this, it will really help lay out, do the groundwork for coming missions of like the Mars Science Laboratory in 2009 and also the Scout Aeronomy missions in 2013. But tell us more about recent and exciting progress that Phoenix has gone into. What I'd like to do is now turn to the Principal Investigator, Peter Smith.
Thank you, Mike. On behalf of the Phoenix mission, we want to thank you for the extended mission. This is important to us. All our instruments are healthy. We are going to complete the science we set out to complete in our prime mission. However, that science is being done in one location on top of one of the little hillocks or mounds that's in front of us. And we have lots more to explore within reach of our robotic arm. So we are planning to extend 2 new trenches, and this is what we'll be doing in this extra time you've given us. And these trenches will go not just from the tops of the mounds in front of us, but down into the troughs in between. This is important. Those troughs are places where material brought in by winds can collect. As you might suspect, it collects in the low spots. And it's places where we see in orbital images that ice persists for the longest period of time, and therefore maybe a place with a different characteristic than those on the hummock. So the extended mission will be a time to explore new parts within reach of our arm. And if I can have the first slide, I'll show you just exactly where these new trench locations are and their names. We've first dug Dodo Goldilocks on the left, and we're currently drawing samples out of Snow White way to the right, and now we're going to work in between. We're going to start with Cupboard, the idea being that maybe the cupboard is full and this is a place to find new discoveries. And we'll dig from the top furthest away from the spacecraft of one of these little mounds or hillocks, all the way down towards the lander, which is in a trough region. And then we'll also look at Neverland in the center, and this is very close to one of the larger rocks within reach of our arm, and a place where we think the ice table underneath the surface may be modified by the presence of a rock. The rocks tend to get a little warmer than the soil. So this is an exciting time, and thank you very much, Mike. The progress to date has been rather dramatic. We have finished, since the last time we've talked, that we've finished our complete panorama in full color and in stereoscopic view. So we actually have a topography now of the landscape around us, and Mark Lemon will be showing us examples from this wonderful product. We have a weather station that's operated for 65 sols. Vicki Hipkin is going to be talking about that and what we've learned from our polar weather station. And we are following the NASA guideline of looking for water on Mars, and we expected to find water in this landing site. That's why we came here. Odyssey discovered regional water supplies, but we're very pleased to see that we landed right on top of water ice, and the thrusters spread the soil away and revealed ice right underneath our lander. This was unexpected, and this was a wonderful thing for us because the water could have been all around us and not within reach of our robotic arm. We had no way of knowing on the local scale how the ice was distributed. So this has been a wonderful thing for us to be able to dig a trench, the Dodo Goldilocks trench, and find at 2 inches deep that there's a solid layer, and then to scrape pieces of this white solid layer off and watch them sublimate over the course of 4 days. So that was our first indication that this hard material is definitely ice. We have been now looking at the properties of the soil above ice. This is important for modeling this surface and trying to understand the interaction between the ice and the tiny amount of water vapor that's in the atmosphere. And we use a probe on the end of our robotic arm for trying to understand the physical properties of this soil, which are so important to our models. And that's what we've been doing for the last couple weeks. Plus, we've been looking with our microscope at samples of the soil. We see there's a clay-like component, in other words, very small flower-sized particles. And these particles have unexpected properties, as we found when we tried to scoop some up and deliver it to one of our prime instruments. And we are just getting to the point where we can apply another tool in our toolbox, the atomic force microscope, which takes our resolution down by a factor of 40 over the microscopic pictures that we have shown. And this microscope is just about ready to start its mission, and we'll be using this extended mission to do that sort of science. And so I ask for a little patience here as we get to the part of the mission where we do the scientific analysis of the soil in contact with ice. This does take some time, and we still have not collected all our data, so it's definitely going to take some time. And we are looking to understand the history of the ice by trying to figure out if this ice has ever melted, and through melting has created a liquid environment that modifies soils, changes chemistry, changes the microscopic appearance of these soils. And we're just getting the data back in the last week or two, and even, as you'll find out, very recently, yesterday. So this is an exciting time, and through this analysis we also hope to be able to answer a question that goes beyond just finding water ice, but is this a habitable zone on Mars? A habitable zone meaning that we have periodic liquid water, not today but over time, and we have the materials that are the basic ingredients for life forms. It'll be for a future mission to find if anybody's home in this environment, but we will be finding if this is a place that needs to be searched for life forms throughout the next 2 months of our approved mission. So far we've had 2 wet chemistry analyses completed. We see that the soils are alkaline. This is a mystery. We're on the edge of a volcano. This is typically an acidic environment. Certainly the 2 MER rovers have found lots of evidence for sulfates and acidic environment. We find an alkaline environment here. Perhaps it has something to do with that nearby crater that impacted into this ice-rich soil and spread out a ejecta blanket that we are landed on top of. So that I don't know for a fact, but that's a possibility. We're also finding nutrients, sodium, potassium, magnesium, chlorides. All of these things are things that we find in our own bodies and are definitely nutrients that are important for life. However, we have yet to discover organic materials. But the important thing is that we have used our snow white trench to try and get a sample of icy soil into our TIGA instrument. And first we did it by using the blade on our scoop to scrape down to the very hard materials where we could go no further. And then we have a scraper, and we've been using this scraper, and then finally a rasp. And I have a series of pictures to show this process that's taken place over the last month or so. So if I could see the first slide. This is the ground before we ever touched it with our scraper. Next slide, we did a simple 1 scoop wide trench. Next slide, please. Yes, and then the pile of the scrapings is behind it, or the digging is behind it, and it makes a little mound. And then we, next slide shows, I think we go to 2 scoops wide. So since we can't go any deeper, we have to go wider. There's 2 scoops wide, and to the left is a little scoop taken out. That was delivered to the Mecca instrument. Let's keep going. Next slide. Look at this. At the bottom, we now see a dark patch after scraping, and that dark patch we consider to be ice, and it changes its properties over day by day. It goes kind of bluish, and then it goes whitish, and then it turns reddish. It's quite an amazing process as this ice sublimates away into the atmosphere. In other words, goes from solid to vapor without being liquid. Next slide. Shows further scraping on the soil, and the piles are getting bigger. Next slide. We extend the trench to be twice as long so that we can do the kind of activities in here we need to do to try and get samples of this icy soil. Next slide. There's a pattern. You see a 4x4 pattern of tiny little holes in the ice. This is caused by our rasp on the back of the scoop pressing against the ground and spinning out little cores of icy soil. And it's done in a beautiful way. The robotic arm team has just mastered using this tool, and they've made a 4x4 grid here, filled the scoop with about 3 cc's of icy soil. And next slide shows the latest, where we've scraped that material off the surface and actually successfully delivered it to TIGA. And to tell us about the TIGA sampling and what we're learning so far from the TIGA is the lead scientist on that instrument, Bill Boynton.
Thank you, Peter. Well, I'm very happy to announce that we've gotten an ice sample into the TIGA oven. When we first found this out yesterday, we were really pleased. There were champagne corks popping in the downlink room, and we just had a great time of it. It's something we've been waiting quite a while for. Of course, we know the GRS on Mars Odyssey discovered this ice 6 years ago, but we've now finally touched it and tasted it. That's one thing that hasn't been done before. And I'd like to say, from my standpoint, it tastes very fine. I'm very glad to be in this position. At this point, I'd like to show a little video of exactly how this process works, how we get the samples delivered to TIGA. This is an animation of the lander, shows the scoop on the robotic arm. It comes down over the TIGA instrument, pours it onto a screen. We then have a vibrator that vibrates it. Here you can see a cutaway drawing. There's, you can see the doors on the top. And there's a little thing we call a whirligig that actually shakes the soil down into the oven. The oven then moves and gets connected to the mating half of the oven. We heat it up, and the gases that are generated are passed on to the evolved gas analyzer. So that's the process that we've been going through. And as I say, now we're at that point where we're starting an analysis of what turns out to be an icy soil. Now, there's not very much ice in this, and in fact, the reason for that is we had tried several times to collect an icy soil, and as Peter described, quite a few weeks, maybe even a month, were spent trying to figure out exactly how to collect an icy soil using the rasp, and we finally got to the point about 5 days ago where we were pretty sure we had perfected this technique. And everything worked fine. We got a great sample in the scoop, and we went to deliver it to TIGA, and it wouldn't pour out of the scoop. It just stuck there. And of all of the things that could have gone wrong, that was the least likely on anybody's list, that it just wouldn't fall out of the scoop. So a couple of days later, we tried again, did things a little bit quicker with the idea of maybe if it might be possibly melting due to heat generation, that we'd do it quicker and it might fall out. And still, the second time it didn't work. So we finally decided, okay, we've got to get on with analyzing just the dry soils, because there's a lot of interesting science there. So we decided, while other people were working on how to deliver the ice, we would actually take a dry soil and analyze it. So we came in yesterday morning hopeful that we'd see a signal that the oven had closed and we'd collected a sample. And indeed we had that, so we're happy about that. But then when we started looking at the data, we realized that we got a little bit of ice mixed in with this sample. Now, it's not a lot, and we haven't yet completed the analysis to know exactly how much. It's probably at most a few percent, maybe even quite a bit less than that. But nevertheless, we did finally get some ice, and so I'm happy to go beyond that point. Now, the way we detected that ice was in there was by noticing the melting. When you heat up material that has ice in it, once you get to the melting point of the ice, it takes a lot more heat in order to melt the ice before you can raise the temperature. And so that's what we saw. We actually saw the melting of the ice. What we'll be doing in the next week is heating the sample up to ever greater temperatures to look for different minerals that have various reactions, giving off water, carbon dioxide, other things at higher and higher temperatures. And it's probably going to take us 3 to 4 weeks after that before we get all of the data analyzed. But one of the things I wanted to point out is that, as you probably are aware, we apply names to these features based on fairy tales. And in this particular case, since I was very certain we were going to get a sample into the oven, I decided to name this one Wicked Witch. And that was named after Hansel and Gretel, with the idea that that witch saw her final demise by being pushed into an oven. Well, in this case, if you excuse me, I have to put on the appropriate regalia for this moment. I hope my daughter's not watching, but... So it turned out that probably it would have made more sense, rather than naming this after the witch in Hansel and Gretel, to name it after the Wicked Witch of the West in The Wizard of Oz. And the reason for that is, some of you may know, when she came to her final demise, she said to Dorothy, "You cursed brat, look what you have done. I'm melting." So now I'll pass things on to Vicki, who'll talk about water in the atmosphere and other things.
Yeah, thanks, Bill. Yeah, so from ice in the soil to ice and cloud in the atmosphere. So Phoenix is giving us the first detailed information about weather in the Mars Arctic using a new and very capable combination of science instruments. And we've heard a little bit about that already. There's the MET station on board. There's the special unique opportunity given to us by coordinated observations with the Mars Reconnaissance Orbiter. And I'll also talk a little bit about how we're using all the instruments on the Phoenix lander to give supporting measurements that help us interpret what's happening in the atmosphere. In today's update, I'm going to talk about a summary of our weather observations from sols 1 to 63. And where we are now, we landed in the late springtime on Mars, and we have been following the late spring through into summer. We're now at Sol 65. We're in high summer on Mars, and we're heading towards Sol 74, which is the peak of when we expect to see maximum water vapor around our site. And this has been from the sublimation of the water ice in the North Polar Cap and its transport southwards towards us. So this is, for atmospheric science, the longer this mission can last, the better. And we can really start to follow seasonal changes and understand the very complex picture we have. What I would like to report on first is something that we've been very, very pleased about. What's new to report is that spacecraft power has actually been very, very good, and it's allowed us to extend our atmospheric measurement set into the nighttime. Now, because we're in the high Martian Arctic and we're in summer, that the sun doesn't actually go down below the horizon, but it dips very low, and it does give us darkened skies. And we took a very special measurement on Sol 61. Again, something we really didn't expect ever to be able to do. What we've been able to do is look upwards with the surface stereo imager and actually image the Met LiDAR beam. So what I want to show you now is an image of the Met LiDAR beam that's been taken in a green filter with the SSI camera. And if we could bring that up, please. So this is absolutely an amazing image. What we're looking at here is essentially a laser light show on Mars taken with an instrument with the power of a 30-watt light bulb. And we are seeing that from 200 million miles away. You know, this is absolutely astounding. Now, you know, as well as being a very, very cool image, this is also a kind of a regular image in our atmospheric science data set in terms of what we're looking at. We're looking upwards, and we're looking at, we've got the LiDAR beam in front. It's the first time we've ever done that. If we could go back to the LiDAR beam, please. But behind it, we can see essentially movement of the dust in the sky moving past the beam. This is at some kilometers further back. We're able to see the first 1.5 kilometers of the LiDAR beam as we're looking up in this steep angle. But we're able to see the background sky, and from the motions that we can see there, we can estimate wind direction at height, which is an important measurement for us. What we're also able to do with the combined LiDAR beam and the SSI image here is where the pixels overlap with the LiDAR beam, we can actually extract useful information from the SSI image that will help us with the composition of the particles, things like that. So this is an exciting addition to our atmospheric data set. And what I would like to do now is just go on to our summary report of what we're seeing overall at our landing site. And again, just to put us back in context, we have been looking late spring through to midsummer now. And to remind you of all the different types of instruments we're using, we're making daily measurements with our MET station, and that includes pressure and temperature measurements, winds with the telltale sensor, and our LiDAR to give us vertical profiles and information about the dust and the cloud structure. We're also combining that with our Mars Reconnaissance Orbiter special coordinated observations, which we're trying to do every 10 days or so, to actually look down in the same column of the atmosphere. This is going to be a very, very powerful way of extending what we learn at this single site to what's actually happening over the whole Arctic region. The other instruments that we're using SSI in combination with the MRO passes there to give us water column information and also tell us about the dustiness. But we're even using the robotic arm. So on the days when it's having a rest from digging, we're actually using it with a TECP sensor to give us near-surface profiles of humidity and winds. So it's really a very comprehensive and quite a complex data set. We're even looking at things like dustfall with the optical microscope with MECA. So this will be put together over a long period of time. What I'd like to highlight now is the very regular measurements we've been getting over this period. We did expect the summer period on Mars and the high Arctic to be fairly calm, and we haven't seen any major weather systems pass over our lander at this time. Temperatures, the maximum and minimum, we're seeing big changes throughout each day, but we're not seeing significant changes day to day. And that goes for all of our measurements, apart from pressure. And here I want to highlight two types of observations we're seeing. With pressure, we're seeing a slow daily decrease in pressure, and this is to be expected. What this is related to is the condensation of significant part of the carbon dioxide atmosphere on the southern pole, which is actually in winter just now. And it's quite remarkable, though, though this is an expected result, it's remarkable that we're actually able to measure this change at the high Arctic in the north. And that's been quite interesting and exciting to see. The other thing I want to talk about is our telltale measurements. And because we've had such steady conditions over this mission, what we've been able to do is we're able to combine the measurements we're making on several successive sols to give us a picture, a detailed picture of what's happening in a typical summer Martian sol. And if you bring up the animation now, what we have here is we've combined our measurements. These are 2-minute measurements spaced apart, and we're looking from 10 a.m. on a typical Martian sol through to 6 p.m. The telltale is about 4 inches high. It's about 2 meters off the ground. And what we're looking at is the little mirror in the bottom of the image there. The X you see across it, the bottom right-hand corner is actually indicating north. So what we see over this day is we see the winds are starting being kind of southerly. We see the deflection of the little bob in the mirror telling us which direction the winds come from and how much it's deflected. We've actually calibrated to give ourselves a fairly accurate measurement of wind speed. So we're seeing the winds change direction over that day from starting in southerly, moving over towards westerly, and we actually, if we fill in the day through the night, we actually see that go over to easterly, and that's a weather pattern that is what we would kind of expect to see. The maximum wind speeds we've seen are about 7 meters per second or 15 miles per hour. And what we really want from the wind information, it's kind of critical to helping us understand what the transport is in this whole area. So where the wind is coming from tells us a lot about how to begin to interpret the data we're getting at this landing site. And what I'd like to do now is move to an image that is going to show us how local topography might be influencing what we're seeing. So how the landscape might be actually influencing the wind directions we're seeing, and how much our local site is responsible for the patterns we're seeing in the data, and how representative we are of the whole region. So we landed in Green Valley, and we've now zoomed into Green Valley. This is a very shallow valley in a very flat region. We wanted to go to a very flat region. This is very good for a number of reasons. It's very representative of a large area, so we can extend the measurements we're getting at our landing site and feel that it's representative. It's also for making it for landing reasons we wanted to go somewhere flat too. So we weren't looking for steep topography. And the valley sides here are about 250 meters high. The valley's indicated in blue. And what we actually find with our wind speeds is, especially those easterly nighttime winds that we've picked up, we're actually seeing that the local topography, despite this great flatness, is actually having some influence on the data that we're getting. We're seeing slope flows down the valley sides are actually influencing our landing site, even though, as you'll see, it's very flat. These very shallow slopes of 1 to 2 degrees are enough to actually give us these nice cool breezes. We see the cold temperatures at night in the temperature data as well. And this seems a really good point. Now we've got the context of our landing site to pass the mic over to Mike and to tell us about the panoramas and our wonderful imagery that we've seen. And you'll even be able to see on the horizon some of those valley sides, I think. So I'll pass it over to you now.
Well, I'm here to talk for the Surface Stereo Imager. Peter mentioned a product that we've been working on. We have a requirement for mission success to produce a color panoramic view of our landing site. That color view is done, and I will show it to you in just a little bit. I wanted to talk first a little bit about how the Surface Stereo Imager, the SSI, takes pictures and puts together a panorama like this. I think most people watching are familiar with digital cameras. Maybe you have a 3 megapixel camera or a 7 or a 10 megapixel camera at home. Well, SSI is a 1 megapixel camera, which has been basically the state of the art for landing on Mars right now. But that 1 megapixel works pretty hard. If I can bring up the first illustration, it shows how the SSI works. It has an advantage over a normal digital camera in that your camera at home probably takes pictures getting all 3 colors at one time. It spreads out the 3 megapixels or 10 over 3 different colors. SSI takes 1 picture at a time using the 1 megapixel for the red image, the green image, and the blue image. And those 3 images are sent down to Earth, and then we colorize them, color code them and put them together, and we've got a color view of something in front of us. And an image from SSI is about the size that's being shown right now. It is a very small fraction of our overall landing site. So to build up a panoramic image, we take many, many images and put them together. In the course of getting a panoramic view of our site, we took over 100 different aiming directions. 500 different pictures were taken as part of this panorama. 400 of them were used to make the color combinations, and an additional 100 were used to make digital elevation maps, as well as to make anaglyphs and other ways of visualizing in 3D the site. These 400 pictures that were put together in a color panorama were painstakingly stitched together by the Multi-Mission Image Processing Laboratory at JPL and form a larger mosaic. The whole product took something like 30 sols to accomplish from the beginning to the end. We didn't take pictures on every single sol that were related to this. We had many other things to do with the camera besides take this picture. But over the course of about a month, we took these pictures. They add up to 150 megapixels in the image that will come up in just a moment. It's 100 megabytes worth of downlinked data from the spacecraft. That may not sound like a whole lot. You probably have thumb drives that could easily hold this entire downlink volume from the spacecraft for your computer. However, from our point of view, the scale is it took the equivalent of 15 separate relay passes, communication windows with the orbiters, to downlink this whole panorama. So we put a great deal of effort into it. So now I'd like to show a view of the landing site. This is the color panoramic view that's going to come up. And what we see is a landscape that is coated with dust. It's dotted with rocks and ridges here and there. Essentially, it's an ice-dominated terrain. Phoenix, as you may know, started with Odyssey observations showing permafrost over the northern polar areas. Those observations were not highly specific. They would tell you, within hundreds of kilometers, there's a lot of ice in this region. Mars Reconnaissance Orbiter followed up in looking for places for Phoenix to land, showing that there was this terrain of small hillocks and little ridges or little valleys in between them that Peter described throughout the area, and very few large rocks, a safe place to land. So now that we're on the surface, SSI shows these same features, the shallow troughs. These are believed to indicate ice underground. So the Odyssey observations indicated there was ice. The observations of the polygonal terrain with the hills and valleys indicate that there may be ice underground. On the right side of the image, you see trenches that have confirmed that there is water ice underground in this region, both on the trench that is the left of the two that are shown nearer the center, where we saw water ice sublimate away, and the trench that Bill Boynton just discussed, where we actually sampled and brought the ice into the TIGA instrument to measure. So the basic idea of the panorama, the reason you would take something like this is it provides context for understanding how these trenches fit in their environment, and it lets us also go on to pick interesting areas to examine with more detailed pictures. So now I'd like to zoom into some of these features and show you a brief tour of our site. So we're starting over on the left-hand edge, and we'll just show some features. You see the heat shield and two of the large rocks around here. Those large rocks are very few and far between. You see many, many more small rocks. But the first thing you notice in looking at broader views is this dust that dominates the terrain. This is wind-transported dust that we find all over Mars, and it gives this rusty brown color to everything. There's not a lot of color variation other than where we've dug a hole and exposed the water ice. But the rocks themselves are interesting. They tell a story of slow change at this site. There are many more small rocks, as I mentioned, compared to the big ones. That's kind of a surprise since we landed to see that. While it's going by, you see the hills that Vicki mentioned off to the south and the telltale that we were just looking at. But these rocks that you see dotting the landscape have spent millions to billions of years at the surface, potentially. This is an old landscape. These rocks should be wind sculpted. You go drive around Tucson and you see wind sculpted rocks all over the place. However, we don't see that as much. We see many volcanic rocks, rocks with pores and holes all over them. We see blocky rocks that perhaps came from the Heimdall crater impact event. We see rounded rocks, which may be very old rocks. Some, but very few of them, show obvious signs of wind sculpting. So a puzzle for us is to figure out why that's the case. One of the things we're looking at is whether it's just CO2 ice burial. This area is covered by carbon dioxide ice over the winter. Or it's the rocks themselves cycle through the polygons and spend part of their life underground and come up in a different orientation. So as we look through our workspace, you're seeing more, in addition to the trench that just went by, you're seeing some of the rocks that are immediately in front of us. So with Phoenix, we will also be looking for smaller scale change. The rocks are telling their long-term story. Phoenix can look at some fraction of seasonal scale changes by looking at these trenches that we've created in the areas around us. The images that we have in this panorama were taken at the warmest time of the year. So we're expecting later in the mission, later in the Martian year, frost will appear. We think we've already seen the first glistening of water ice frost in the snow-white trench. But eventually that water frost will give way to basically a winter wonderland of carbon dioxide frost that will be the end of the Phoenix mission in many months to come. So a question after we've now finished this panorama, we have this context to look at, to put everything in its place, to see the different sorts of rocks. What next? We've certainly used this panorama already. We completed it essentially on Sol 43. We've spent about 20 sols getting more detailed observation of some of the more interesting targets, including both the hills and valleys, the polygonal terrain network, and interesting rocks. So we've taken these detailed observations that we'd hoped to do once we had the context imaging. But now we're moving on. The mission, we don't know exactly how long the spacecraft is going to last. Everything is looking very healthy right now. So we thought we would come up with a panorama that would give us the best possible look that we can get back down to Earth from this spacecraft, and said, okay, if we had until the middle of November, how good a panorama could we take? And we designed that panorama. Now we don't have any guarantees, so we're taking the highest priority images first, so that if we have through August or through September, we'll get as much good stuff as we can. But we're taking a panorama that we've named in keeping with the theme that Peter mentioned, the fairy tale theme that goes with this mission. It's the happily ever after pan. It's the panorama that we'll sort of go out in style with. The first panorama we took was the minimum mission success panorama. We finished on Sol 3. The full one that I just showed is 100 times more data volume. The one that we are just starting in is 1,500 image taken through all geology filters at high quality, and altogether it'll be 2/3 of a gigabyte of data to transmit from Mars to Earth, which is nearly 100 orbiter passes. So this is the sort of thing where we'll take one very small section of it at a time and just add it up over as long as we can keep on taking this panorama. So that's where we're going next with the imaging of this site and the detailed investigation of the things we see in front of us. Now I'll throw it back.
Thank you, Mark. Thank you, panel. That was terrific. Now we're going to go to questions. We'll start here in the theater in Tucson. When you get the microphone, please say your name and your organization. And let's start with Alan right here.
Dr. Boynton, this is a question with a follow-up for you. We had a situation where sublimated ice was seen, or sublimated material was seen as proving that there was water ice on the planet. You've said today that you had some ice samples in Tiga, and you described how the energy differential showed that that material was ice as it was being heated up. Has Tiga shown that there's a chemical composition of ice? Has it been able to sniff the material to prove that there's H2O in that sample at this time?
We did get a small release of H2O molecules we saw in the evolved gas analyzer. The fact that it melted at 0 degrees Celsius leaves very little doubt but that it is standard water ice H2O.
So we have Peter Smith. There's still doubters out there based on the sublimation. Have we quelled those doubters at this point?
I think so, but
okay.
There's some doubters that no matter what you do, you can't quell. So
okay. And then as a follow-up to that, in terms of this sample that you're analyzing right now, will you be able to use that sample to find some of the impurities in the ice and also some of the other materials in the soil, the building blocks that was talked about this morning, the hydrogen, the carbons, or will we need to go elsewhere for that test?
We'll do both. We'll first take the sample that we have in the ovens now, and we're going to heat it up about 4 more times to different temperature ranges each time. And we're doing that to see what else we can see that's in the sample. So one way to look at it, you can say the soil is the impurity in the ice, but really in this particular case, since it was probably 99% soil and maybe just 1% ice, you could almost say the ice is the impurity in the soil. But nevertheless, we will be doing the soil analysis here, and in the future we'll be comparing our results on this sample with a well-documented surface sample, looking also at samples taken from the other trench that Peter was talking about. This particular trench is taken in the center of one of these polygons. We're now sometime in the future we'll be sampling these troughs that are separating the polygons. So we'll want to make that comparison.
Dave Perlman here.
Dave Perlman from the San Francisco Chronicle. Early on, there was a good deal of difficulty in getting anything into Tiga. And now, could you describe in some fashion how you managed to get some proportion of ice as well as soil into Tiga? Was there any difficulty in trying to move that material in such a way that you had actual water ice in Tiga that you could then manipulate, and I assume will continue manipulating it unless it all sublimates?
Well, I guess the observations were that it wasn't difficult to get the ice into Tiga because we actually didn't expect any ice in the sample that we were collecting. It was just a quick scraping of the surface, and we were intending to just analyze the soil that was right above the ice layer. But nevertheless, we did get a little bit of ice in there. What we found initially, as you may know, we had some problems with the very first sample getting it into the oven, and that was because it was delivered in the form of one big, essentially, glob of dirt, and this dirt is very cohesive and it's stuck together. We've since realized that we need to kind of sprinkle the soil onto the screen gently, and that's what we use this time, and that's what we'll use for all future deliveries. So we're not anticipating any problems in that area. I'm reasonably confident that once we work out the difficulties, whatever they may be due to why the soil won't fall out of the scoop, we'll probably be able to get a sample that's far more ice rich than this particular one. But I'm not sure I answered all of the question. But
to follow that up, Bill, does the ice itself contribute to the clumpiness, stickiness, difficulty of getting that material into the ovens?
That's a very good question, and that's one of the things that the scientists are tossing around now. The soil has very interesting physical properties, and by studying these physical properties, we can tell something about the nature of the soil, and the clumpiness is certainly one of the more interesting of these properties. One of the hypotheses we have is that there's salt in the soils on the grain surfaces, and in which case then the ice would contribute to the clumpiness. For example, I've been told there are cities up in the north, when they get ice on the roads, they actually sprinkle salt on it to make it melt. Can't imagine why, but anyway, so clearly if you have salt in contact with ice, it melts at a lower temperature. And so what might be going on here is that we've got salt grains on the surface of the soil grains in contact with the ice, and just at that points of contact, it might be melting the ice at very low temperatures, maybe -30 or something like that, giving just a little bit of stickiness to it. So that's one of the hypotheses, in which case, yes, the ice is really contributing to the clumpiness.
And without trying to monopolize the business, is it possible now that you'll be able to take a hard look at some of this water ice and determine whether there are impurities in it of various kinds, whether it happens to be organic impurities or not is another question?
Well, at this particular location, we won't, if we see some of these things you might call impurities, whether they're organic molecules or whatever, we won't really be able to say whether it came from the icy part of the sample or the dirt part of the sample. Now, if we've analyzed, as we expect to, some different samples, and if an ice-rich sample has more of these impurities, then we can associate it with the ice. If the ice-rich sample has fewer of them, then we might be able to associate it with the soil part of the sample. But for one particular sample, we can't tell from which part of it the various minerals or impurities come from.
Thanks, Bill. We're going to move to Houston and a question on the telephone. Can you say your name and your organization, please?
Yes, this is Mark Carreau, and I'm a reporter for the Houston Chronicle. I had a question about the TIGA system. I think I'm counting that there's still 6 ovens left, and I wonder if you could sort of explain your strategy at this point for using them I guess at the site you're at or in the 2 trenches you plan, and could you sort of update us on the electrical short issue that arose earlier and whether that's still a threat or not a threat to using all of the ovens if you plan to?
Okay, I'll comment on the second one first just because that's the easier. We did have a short developed early on. We are reasonably confident it came from one of the solenoids that we're using to work the vibrator. We had to run the vibrator quite a bit on that very first soil to get the clumpiness to break down, and somewhere along that line we think the vibrator overheated, maybe some of the insulation broke down, and one of the wires touched the chassis. Turns out that short circuit has actually disappeared, probably because the wire that was touching the chassis has simply moved, whether it's due to vibrations or thermal cycling of the instrument, but whatever, that short has disappeared. That particular short wasn't of much of a problem. Any event, we could still operate the remaining ovens, but right now we feel that that's not really much of a problem whatsoever. We are operating the solenoid differently now in that we're never going to operate it for more than 3 minutes at a time, followed by at least 3 minutes of cooling. This will ensure that the object does not overheat again in the future. Now, getting back to the first part of the question, maybe you better remind me what it was.
Future cells.
Oh, future cells. Thank you very much. Yes, what we do have plans laid out for the future cells. The next one is going to be a surface sample. We've already had one surface sample, but this was taken in an area where we've got good reason to believe there was a lot of mix-up with stuff thrown up from the rocket motors when we were landing. We want to go to a place right near Rosy Red to get a sample taken from essentially the same location as the one that went into the wet chemistry lab for its first sample. So that's going to be our next one. Then we'll go over to the, well, the order may be up for discussion where we go next. We might then go back to Snow White and get a higher concentration of ice sample if indeed the technique for delivering those samples has been worked out by then. Other samples we're going to do is we're going to go into the trough area and get a couple samples from there. We want to save one of the ovens for analyzing our organic-free blank. In the event that we're fortunate enough to detect organic molecules, we've got a material we brought along with us which is designed to be free of organic molecules. And one of the things we want to do, of course, is if we detect organic molecules in the Mars sample, we want to be able to say with some confidence that it's not just contamination we brought with us. We built the TIGA instrument and the robotic arm under very, very clean conditions, but you can never tell for sure that you don't have some very modest amount of contamination. So we are going to reserve the one of the TIGA cells as a blank to make sure that we understand how much organic contamination we might be bringing from Earth and how much could be coming from Mars.
Mark, go ahead with your follow-up.
Thank you. I think I did count in your assessment still 6 ovens, and I'm wondering at this point if that's correct, do you still have a good shot, do you think, at trying to find organics if they're there before the extended mission ends? And I'm also wondering, is part of the reason for extending the mission to give you a chance to do that since you're 2 months into the project?
I think we'll actually be able to to do as good a test as we can looking for organic molecules, I think, before the mission comes to an end. We're learning as we go along the best way to heat the soil and the different properties that we are finding, and we have ways of fine-tuning the instrument to make it more sensitive for organic molecules at the expense of other molecules. Now, the reason for getting the extended mission is not just so that TIGA could fill out and analyze the remaining ovens that we have, but for many other reasons that Peter noted early on. But certainly it's going to be very helpful to have more time to complete the analyses, and with the idea of using all 8 of the TIGA ovens.
Thanks, Bill. Next, we're going to go to Craig. Sorry,
Can I
Vicki?
just comment as well?
Certainly.
I didn't say this on the atmospheric analysis, but of course the extended mission is very important for understanding the seasonal variations here. We've had this calm period over the summer, and we're expecting to see much more in the way of dust and cloud activity as we go later on in the season. So we're really looking forward to that on the atmospheric science part of the team.
Thanks, Vicki. Next, we're going to go to Craig Cavalt from Aviation Week and Space Technology. Craig?
Yeah, hi. Thanks very much. I don't see the Mika guys there. Are they hiding under the table, or? So could you tell me about the data from the second Mika wet test? Are those data provocative? And if so, why? And for, I guess, Mike there from headquarters, have you at least notified the President's Science Advisor's office that you're looking at what you're going to tell me about you're looking at? I hope.
I don't know what I'm going to tell you you're looking at. We have seen the salts inside of the MECA wet chemistry cells. The 2 cells give a very similar description of the soil chemistry, and they're taken from the surface sample and a sample above ice. We purposely tried not to put ice into MECA since it adds water to the sample, and therefore you would have less of the ingredients that it's able to analyze. There are some signatures in there that have not been interpreted yet, and we are still working on the analysis of those, so it's too early for me to say what else we have in there besides the salts and the alkalinity that we've released. Probably over the next month or 2 we'll be able to understand fully what we're measuring in the MECA cells.
Just as a note, I mean, it's one of these things where the soil is turning out to be different than what was expected. You know, it's alkaline and it has these salts in it. So it's a substance that we're not familiar with, and it's different from what the Mars exploration rovers have found. So not only waiting for the MECA results to be analyzed, but also how does that corroborate with the results from TIGA. So there's a lot more work that needs to be done before we have any kind of real conclusion as to what's in the soil.
Next, we're going to go to Kate Tobin from CNN. Kate?
Yes, this is Kate. Can you hear me?
We sure can.
Okay, excellent. This is a question, I guess, for Bill Boynton. You indicated that for the sample that is now in the TIGA, take about a week of baking and then 3 to 4 weeks of analysis. Can you talk through a little bit more about that process? How long does it take to get the data down? What happens once it gets on the ground? And could you give us a couple of examples of the types of compounds you think you might see?
Sure, I'd be glad to do that. The standard way we look at the samples is the first day, which is the day that's already been completed. We heat the sample up just a little bit above the melting point of water ice. We heat it up to about 35 degrees Celsius, a little bit warmer than room temperature. And so at that point we look to see if indeed we find ice based on the melting, and in this case we did. And the other thing we do is we spend about 90 minutes drying out the sample in case there is any water ice in the sample. After we melt it, we want to get rid of the water. So at the end of that first day, we're actually drying the sample. On the second day, we typically will bake out the mass spectrometer, and the reason for that is we may have gotten a lot of water introduced into the mass spectrometer, and water is one of these molecules that tends to stick to different surfaces. So we try to work pretty hard on pumping those molecules out so they don't interfere with subsequent analyses. On the third day, we'll do a ramp where we heat the sample up to about 175 Celsius. The reason there is we expect that there may be some oxidants in the sample. The Viking instrument, for example, wasn't able to find organic molecules, and one of the hypotheses is that there's some strong oxidant in the soil, and so we had always planned on heating it up to temperatures in the order of 175 that might decompose some of the postulated oxidants. After that, we then heat it up to some intermediate temperature. It's kind of a to-be-determined temperature where we might suspect organic molecules to be coming off. And so we look very carefully at that particular temperature that we choose for organic molecules. The day after that, we heat it up to 1,000 degrees Celsius, which is our maximum temperature. And then the day after that, we heat it up to the same temperature to get a baseline to subtract from the previous day. So it's a pretty complex process to go through the entire analyses. And then, of course, once we get the data, we have to kind of split up our time between looking at the data and planning for the next sample and doing all the data reduction. So we're going to be some pretty busy boys and girls for the next few months.
I think we have time for one last question from Todd Halverson from Florida Today.
Thank you very much. I have one and a follow if I could. The first, I think, for Mr. Myers from headquarters. Could you give us a estimate on the cost of extending the mission? And then I have a follow, please.
Yeah, certainly. To extend the mission to the end of the fiscal year, we're putting in something on the order of $2 million, and that should take it through the end of September 30th.
And your follow?
Chronicken, you know, I'm just thinking back to the United States restarting its Mars exploration program back with Pathfinder in 1997, and that was sort of the start of this hunt for water. And I'm wondering if you can put in perspective just how big a deal this finding is.
Well, I have to say that it is one of those things where we've gotten to the point where we're pretty sure we found water, and then actually be able to measure it as H2O really helps conclude part of that search. And I think one of the things that we're seeing with Phoenix and what we'll see with future missions is that we'll be moving away from necessarily finding water, but to actually looking for where there might be habitats for life. And so part of that indicator is the fact that TIGA is going to be able to measure organic molecules. Next mission, the Mars Science Laboratory also has a gas chromatograph mass spec. So we're moving toward to understanding whether or not there are places on Mars that could have been or might even still be habitable.
Dick Kerr, if you can ask your question quickly and we can get a quick answer, we will go to you, please.
Boynton, this is Dick Kerr at Science. What's the possibility of getting some isotopic compositions on that water that you got into this particular cell, if it's a few percent or less?
Okay, in this particular case, it seems pretty clear that there's not enough there for us to get a good isotopic signature. The amount of water is really at our detection limit, and we really need more than that to be able to measure the isotopic ratios. Those ratios need to be measured with very high precision to be useful, as I think you probably appreciate. And this particular sample doesn't give us enough material to do that, which is why at some point we will have to go back and get a more ice-rich sample.
Well, thanks, everyone. Thanks to the panel for your great answers and great news today. Thanks to the audience and you folks tuning in. We hope to see you again soon. In the meantime, you can follow our progress on our websites. And happy birthday, NASA.
mit einer Bodenprobe Wasser auf dem Mars nachgewiesen. Fündig wurde die Raumsonde Phoenix mit ihrem Roboterarm. Beim Erhitzen der gefrorenen Probe sei dann Wasserdampf entstanden, so die Wissenschaftler. Die Existenz von Wasser gilt als Voraussetzung für mögliches Leben auf dem Mars.
Dem Planeten nachgewiesen. Frühere Mars-Missionen hatten bereits Hinweise auf Wasser ergeben. Der endgültige Beweis fehlte aber bislang. Wie die amerikanische Weltraumbehörde NASA mitteilte, gelang nun der Nachweis in einer Bodenprobe.
Was auf den ersten Blick so unwirtlich aussieht, trägt auf den zweiten die Grundlage jeden Lebens in sich: Wasser. Der Fund auf der Marsoberfläche historisch, die NASA in Feierstimmung. Wir haben das Wasser berührt und geschmeckt. Das gab es noch nie. Wir, das sind in diesem Fall nicht die Wissenschaftler, sondern es ist die Raumsonde Phoenix. Mit einem Roboterarm hat sie die gefrorene Bodenprobe gesammelt und im Ofen des Minilabors erhitzt. Dabei entstand Wasserdampf. Ebenfalls an dem Roboterarm befestigt, Technologie aus Niedersachsen. Eine Spezialkamera des Max-Planck-Instituts in Katlenburg-Lindau. Sie fotografiert die Proben zunächst, bevor sie analysiert werden. Die Technik ist so etwas wie das Auge der Sonde.
Sie ist auch wichtig, um etwa den Aufbau, die Struktur des Bodens festzustellen, denn daraus können wir eben lernen, wie das Wasser dorthin gekommen ist, etwa ob es Schichtungen gibt, Hinweise, dass es mal geflossen ist und so weiter.
Der Nachweis von Wasser beflügelt die Fantasie der Wissenschaftler. Gibt oder gab es doch Leben auf dem Mars?
Bisher haben wir gefrorenes Wasser, Eis gefunden. Die Fragen sind, wie ist es dorthin gekommen? War es einmal flüssig in der Vergangenheit? Wird es gelegentlich auch heute noch sich verflüssigen und somit Lebensraum für organisches Leben bieten können?
Der Erfolg für die NASA ein Schub nach vorn. Die Mars-Mission mit deutscher Technik an Bord soll verlängert werden um 2 weitere Monate.
Es offenbar Wasser. Das ergibt sich nach Ansicht von US-Wissenschaftlern aus Bodenproben vom roten Planeten, die die Marssonde Phoenix jetzt geliefert hat. Wasser gilt als unverzichtbare Voraussetzung für jede Form von Leben, wie wir es kennen. Indizien für die Existenz von Leben auf dem roten Planeten hat Phoenix aber nicht gefunden.
Good day. My name is Dwayne Brown with the Office of Public Affairs, and welcome to NASA headquarters. NASA's Phoenix Mars lander, which arrived on the red planet in May of this year, has been very busy. The spacecraft has ended its prime mission and is now in extended operations. And today, you'll get the latest science developments of the mission. We have participants here in Washington as well as the Jet Propulsion Lab in Pasadena, California. We'll have brief presentations, then open it up for questions at our centers and take calls from our phone lines. We've got a lot to cover, so let me introduce you to today's participants, starting here in Washington first. To set the stage will be Doug McQuistion, the Director of Mars Exploration Program here at NASA headquarters in Washington. Joining me on stage to my left is William Boynton, Lead Scientist, Thermal and Evolved Gas Analyzer from the University of Arizona. Jim Whiteway, Lead Scientist, Phoenix Meteorological Station, York University in Toronto. And of course, Peter Smith, the Phoenix Principal Investigator, also at the University of Arizona. And going out to the Jet Propulsion Lab, we have Barry Goldstein, the Phoenix Project Manager. And joining Barry, Michael Hecht, Lead Scientist, Microscopy, Electrochemistry, and Connectivity Analyzer, or MICA. So to set the stage, I'll ask Doug to take the podium.
Thank you, Dwayne. Well, it's an exciting place to be in a mission. Back in 2003, NASA selected its first Mars Scout mission. That's the Phoenix mission. It's been a long 5 years, a lot of work, but here we are celebrating the success of this mission. Its sister ship, the 1998 Polar Lander, was lost in the process of landing, so nobody was resting easily between 2003 and 2008, but we landed successfully in May, and it's been great set of operations ever since. The rovers have been investigating the history of past water on the planet Mars for almost 5 years now. Phoenix is the first mission to actually touch that Martian water up in the northern Arctic. It's created a lot of firsts. It's the first soft lander since Viking. That was about 30 years prior. It was the first mission to the Martian Arctic, and it was also the first mission that actually landed on an ice rink and has gone down and touched that water. Water is very important. The Mars program's theme in the decade is to follow the water. The water is important, is one of the critical elements to sustain life. In our search for life within the universe, this is a very critical element to understand what the history of that is, and Mars is an easy place to get to, relatively, to be able to really understand that cycle. Phoenix has done a great job in helping us expand our understanding of water and climatic processes and the water drivers in the climate. The significant amount of science data collected by the Phoenix mission will last the science research community for a significant number of years to come. As a result, and the success of this mission, especially meteorologically, as we move into the Martian winter, we've decided to extend the mission further. Beginning October 1st, we've extended the mission to try to survive as long as it can. There is an end to this mission because of weather, but we want to see how far we can get the mission into winter and understand the climactic processes that occur. But the little lander is terminal. It's battling the weather and it's battling the temperatures. So as I said, it has a finite lifespan, but the science outcomes and the science data that it produces is going to last a lot longer than its lifespan. To talk a little bit more about the engineering side of this and the future expectations for this, I'd like to turn this over to the Jet Propulsion Laboratory to Barry Goldstein, the project manager. Barry?
Thank you, Doug. Appreciate that. Well, today is Sol 123 on Mars, and we landed, as Doug mentioned, on May 25th, and the vehicle's been operating tremendously well all this time. We originally designed this mission to last 90 sols, and clearly we're doing very much better than that. As it turns out, we've actually commanded this vehicle 120 of the 123 sols that we have actually been on the surface, and that's a pretty good performance record, so the team's doing very well. Although the vehicle is, as Doug points out, somewhat terminal, I can say right now that the health of the vehicle is exceptional. It's doing extremely well. Every day it's waking up as per command and communicating with Odyssey, the orbiter around Mars, as well as the Mars Reconnaissance Orbiter, and doing its job just well. However, one of the things that I was frequently asked before launch and before landing was, well, you've told us before that a mission's designed for 90 sols. We've heard that before, but Mars Exploration Rover is now approaching 5 years. So how can we believe you this time? Can I have the first slide, please? Well, fundamental to our termination of this mission is where we're landing. As you can see where the arrow is pointing, we're way up above the Arctic Circle on Mars. And much like on the Earth, when you're above the Arctic Circle, sometimes during the year the sun is up all of the time. Other times during the year, the sun is down all of the time. And when we landed on May 25th, we landed in the early part, or the early part of the summer, late spring, to try to maximize the amount of time that we would have the sun above the horizon. However, on Sol 93, as it turned out, that was the first Sol that we actually had the sun dip completely below the horizon. And as a matter of fact, we have a video. Can we show this video? This was a video that was shot, a series of images that were taken on Sol 101, which is showing the sun rise above the Arctic horizon. Actually seeing sunrise here. We could play it in reverse and see the opposite. But this is actually what we're facing now. And as it turns out, we can stop the video now. Okay. As it turns out, even though the vehicle was designed strictly to operate during the 90 sols, we know that we have enough energy in the vehicle to survive and continue operating further, and that's why, Doug, as Doug explained, we've extended the mission beyond that. As the Martian winter approaches, and I'd like to show a curve, please. Can you bring up the last slide? As the Martian winter approaches, we lose sunlight. The curve you're seeing here, if you see a green slash, that's where we are today, which is approximately Sol 123. Of the 24 hours and 40 minutes, that's the duration of a Martian sol, the sun is below the horizon right now, a little over 4 hours of that sol. But you can see as that curve steepens out, it's actually going to go below the horizon longer and longer. And eventually, when it gets in, you can see the date annotated there on April 1st, the sun is actually below the horizon for a good 3 months. So by the time we get to April, there'll be no sun up there, and that hurts the vehicle in quite a few ways, which I'll explain in a little bit. However, after the sun starts rising, which is about 3 months later, sometime in the early July time frame, we start getting more and more energy, and the vehicle will probably not survive that, but there won't be enough power on the vehicle if anyone is thinking for it to reasonably come back to life until the October time frame, although nobody anticipates that the vehicle survived that harsh winter. However, one of the consequences of the fact that the sun is going down is we actually have two problems. Number one, we are producing less energy. Obviously, as the sun is low on the horizon and dipping below the horizon, we produce less energy per sol. And the second thing that's working against us as well is we're consuming more energy. As the temperatures get colder and colder, the vehicle has to produce more energy to its heaters to keep the electronics from freezing. So both these things conspire against us and take energy away from the science that we would like to do with the vehicle. So we're trying to literally make hay as the sun shine and really try to get the most out of the science instruments in these last few days before the end of the mission. To put some numbers on that, when we landed in late May, and probably for about the first month of the mission, we were actually generating about 3,500 watt hours every sol, which was plenty of energy to do lots of our in situ or on-surface instrument experiments. However, last Friday on Sol 120, the information we got was the vehicle produced 2,100 watt hours in that given sol, and it's slowly going down and down to the point where we're going to become a weather station with occasional images. But up until that point, we're going to try to squeeze every bit of science out of this mission from now until whenever it is the terminal date. And with that, I'll throw it over to Bill to talk a little bit about the TIGA.
Thank you, Barry. Well, I'd like to talk about some of the really exciting results we're finding with the TIGA instrument. We've identified several minerals that are indicators for interaction with water in the past. Now, some of these minerals have been found by remote sensing via orbiters, but only in areas on the planet where there's been evidence for flowing water in the past. What's new here is that we've seen evidence in the northern plains, kind of in the wide open spaces where there really is no evidence for flowing water. So that's one of the things we're really excited about. But before I go on to talk about those results, I should tell you about TIGA and how it works. It's a somewhat complicated instrument. TIGA stands for a Thermal and Evolved Gas Analyzer. It has 8 small ovens which heat up the soil samples, and it has an evolved gas analyzer which sniffs the gases that are given off as the sample is heated. Now, knowing the nature of the gases given off is actually very useful in identifying what's in the oven. It's very much as if you walk into a kitchen where chocolate chip cookies are baking, and you can immediately tell from your nose what's in the oven. Okay, let me give you a picture now. I can show this first video of how it works. The robotic arm scoops up some soil, and it delivers it to TIGA. Here it's going to pour it into one of the cells containing one of the ovens, and it falls into a funnel, goes past a little rotator thing called a whirligig that disturbs the soil and makes sure it doesn't get stuck in the funnel. And it falls into an oven. We then seal the oven, heat it up, gets red hot, as you can see, and the hot gases are then passed along to the evolved gas analyzer, which tell us what's happening. Okay, next what I'd like to do is talk about the locations where we got our samples. If I can have the first still picture, please. Here you can see a picture of the ground looking down from the imager. Off on the right is just the edge of the solar panels, and you can see 3 little white squares are actually of sunlight passing through holes in the solar panel. The area of interest is the darker part of the scene, right in the middle. You can see where there's a trench where we've actually scooped up our samples. TIGA's analyzed samples from the surface and at several levels of depth. Well, the first material indicative of formation with liquid water that I'd like to talk about was found by TIGA on the basis of a high temperature release of water vapor. It is most likely due to a clay mineral, which is in the class of minerals called sheet silicates. The best known example of a sheet silicate is mica, but in this case we're not looking at mica. We're looking at a different type in which a form of water actually is in the crystal structure between the different sheets. And it's this water which is between the sheets that makes the clay minerals much softer than mica, for example. In this case, our identification is somewhat ambiguous. There are a few other minerals which could release water vapor at high temperatures, but we think the sheet silicates or the clays are probably the most likely. The other important mineral we found is a carbonate. And this also points to the presence of liquid water. It's actually calcium carbonate. And this mineral was identified by TIGA on the basis of a high temperature release of carbon dioxide gas. Now in this case, our identification is unambiguous. The release of carbon dioxide gas can only come from a carbonate, and the fact that it was released at high temperature means it's really the calcium carbonate as opposed to some other forms such as iron or magnesium carbonate. Now, carbonates are very common minerals on Earth. They commonly form by the interaction of liquid water with carbon dioxide gas, and that's just what we think is going on the surface of Mars. Another form in which people are familiar is just common chalk that you use for writing on blackboards, and another use of it is in the form of antacids, where if you have acidic stomachs, you can take one of these things, then it will lower the acidity. Well, in fact, our next presenter, Mike Hecht, is going to be talking about the aspect of calcium carbonate and its ability to neutralize acids, which was actually the basis for identification of this mineral based on another Phoenix instrument, the MECA instrument. Mike?
Thank you, Bill. MECA is a suite of instruments that includes 4 wet chemistry cells, it includes 2 microscopes, and it includes a conductivity probe at the end of the robotic arm. We've been enjoying a feast of data from these instruments for the last 4 months. I'll tell you a little bit about all 3, including additional evidence for the 2 materials that Bill Boynton just told you about. So let's start with the chemistry. Now, one of the first findings we announced at the beginning of the mission was the pH of the soil, which we now believe is about 8.3. That's a little lower than we initially thought in our first preliminary report. That turns out to be almost exactly the pH of ocean water on Earth. And ocean water is that pH because it is held there by a lot of undissolved calcium carbonate by a process we call buffering. One of the ways you know you have a buffered solution is when you add acid, which we do in the MECA experiment, the pH doesn't change very much. And so we saw exactly that response, suggestive of carbonate. And the way we know it's calcium carbonate is that there should be a certain amount of calcium in the solution, a certain concentration, to go with calcium carbonate, and we see exactly that concentration. So indeed, using 2 entirely different methods, the thermal method from TIGA and the solution chemistry method from MECA, we have confirmed the presence of calcium carbonate. And if you combine that with our previous discovery of perchlorate salts in the soil, we really now have enough information between carbonates and perchlorates to begin rewriting the book of Martian geochemistry. Now let me transition over to the optical microscope. When you look at sand on a beach, you see a sea of whitish stuff, and it's not until you look up close under a magnifying glass or under a microscope that you really see all the different mineral grains and types and sizes and shapes and colors that really make it so interesting and tell you about the mineralogy of Earth. The same is very much true on Mars, and I can say we've finally gotten to the bottom of the pile. We finally see what all these really tiny particles look like, what they're made of, what kind of shapes and crystalline forms they have. So we'll start by looking at the first image, which is what we call a through-focus reconstruction. It means we've taken a bunch of images at different focus positions and combined them to make them look like one in-focus image. Now, most of what you see is this reddish orangey, this rust-colored fine powder that we tend to call nanophase iron oxide, because that sounds better than rust-colored fine powder. And in between that, you see all these little darker and lighter, larger particles. I say larger, they're smaller than the width of a human hair, but compared to the fine stuff, these are relatively large. They come in all colors. When you look at these images as they're released on the website in coming weeks, you'll see them in really their full glory, as you see in the second graphic. And you'll find that these are clear, these are red, these are green, these are dark. And in particular, the reason in the second graphic that they're all clustered like that is because they're strongly magnetic. You're looking at the surface of a magnet. All the fine red stuff has fallen off the magnet, leaving behind all these little Easter eggs of all different colors and shapes. Now, in addition to these rounded particles, which we believe are rounded because they've been tumbled by the wind across the sand and they've been polished, you also see a lot of angular particles that are clear, that are very white, as if they're salts, that are in different colors. So we can start to see the different animals in the zoo of Martian mineralogy. That still leaves this red nanophase iron oxide to understand. The particles are too small to see with our optical microscope. They're actually smaller than the wavelength of the light that we're looking at. So fortunately, we have an atomic force microscope that can bring back images of particles much smaller than even a pixel on the optical microscope. And it does that by feeling the surface of those particles with a very fine machine silicon tip. And when we start looking with the atomic force microscope, it's a very difficult process. We have to find the particles first, but we've managed to capture a few dozen like the one in the first graphic. And what most of these have in common, if we could bring up that graphic, please, is the fact that in the upper left you see it's flat and smooth on the top. It has a sharp point. It has a sharp angle. And we see lots of different combinations of these. Sometimes they're stacked up. Sometimes they're different angles. They're often standing on end. But they remind us of what we look at when we see these, what Bill referred to as these sheet silicates or phyllosilicates. There's an example of the phyllosilicate in the lower right that was taken by the Clay Mineral Society on Earth, and that happens to be a denticulated pyroxene. But this family of silicates is not dissimilar to what we're looking at with the atomic force microscope. So what we have to talk to you about with microscopy in coming weeks will be this accumulating kind of a library, this catalog of different types of particles and crystals and salts and hopefully silicates. Now finally, let me talk a little bit about the TECP. It's at the end of the robot arm. We've been busy sticking the needles into soil in different places, looking for signs of ice, signs for liquid water, almost liquid water, water vapor. Now the interesting result here is that we didn't find very much. Why is that interesting? Well, no dampness, no traces of not quite frozen water, not even the humidity in the air above the soil that you might expect just to rise from the warming ice. So in other words, what we've learned from the TECP is that the soil in our little corner of Mars is very, very dry. And with that, I'd like to turn the microphone back to NASA headquarters in Washington. Thank you.
Okay, thank you. So for the past 4 months, we've been continuously monitoring the weather at the Phoenix site. So this has included standard meteorological measurements of temperature, pressure, and wind. We've been taking images of the atmosphere. We've been coordinating these measurements with observations from orbit as much as possible. And we also have an experimental instrument called a LiDAR, which has provided a view of the atmosphere that has never been seen before. And I'll start with just the temperature measured over the mission. So the graph on the screen is showing the minimum daily temperature from Sol 0 landing day up until about Sol 120. And you can see that for the first 2 months of the mission, the temperature was increasing. The summer solstice was at about Sol 30, and then this temperature started to decrease. And now while the temperature is decreasing, we have observed water condensing in the atmosphere. So over the first 2 months of the mission, The humidity of the atmosphere was increasing as water sublimated from the ground in the polar ice cap. And over the second half of the mission, we started to see frost, ground fog, and clouds. And this is now occurring every night. Okay, so the next screen shows images of clouds drifting past the horizon. If we could see the next screen, please. Okay, so this is the view out over the horizon just about every morning now. So this is in the early hours of the morning, and we see that there are clouds drifting by on the horizon. So this is where the LiDAR comes in. So the LiDAR is able to probe the inner structure of the clouds. So the LiDAR instrument emits pulses of light upward into the atmosphere and detects what is scattered back. Now this image shows, first of all, on the right, a graphical depiction of the LiDAR, the laser beam pointed upward from the lander. So at the heart of the LiDAR is a laser. It emits pulses of light 100 times per second, and if you were standing beside the lander looking upward, you would see a continuous green beam. And that is what we're seeing on the left side of this image. That's a picture taken with the SSI camera. And it's actually been, we can go back again. Sorry, okay, so that green beam is a series of images from the SSI camera. And you can see bright spots in the beam, which are actually ice crystals, laser light reflecting from ice crystals. And at the top of the beam, it's brighter because it's reflecting from a cloud, which is a few miles above the surface there. Okay, so in the next image shows a record of the LiDAR measurements over a 1 hour period. So this shows the amount of light which was scattered back as a function of time. So time is increasing from left to right. And the colored area is the outline of a cloud. So this is the strength of the LiDAR. It's able to show us the structure within the cloud. So we're kind of looking at the anatomy of the cloud. And you can really see what the LiDAR brings out on the right side of this figure where the arrow is pointing at fall streaks. So the cloud is composed of ice crystals, and some of those ice crystals are large enough to fall through the atmosphere. And as they're falling through the atmosphere, the wind is changing speed. There's a shear, so it's a different speed at different heights. And these streaks, or fall streaks, get sheared out into the horizontal. So you can see here that the ice crystals would be starting out at a height of about 4 kilometers. And by the end of the measurement, in this case, they've fallen all the way down to 2.5 kilometers. And since while we're taking measurements on Mars, we don't know what's happening. If we had a choice here, we would have continued measuring for another hour. But so I would have expected that the ice crystals would have fallen even closer to the surface in this case. So that is snow falling from the clouds, and we're going to be watching very closely over the next month for evidence that the snow is actually landing on the surface. And this is a very important factor in the hydrological cycle on Mars, with the exchange of water between the surface and the atmosphere. Okay, now to summarize everything, I'll pass it over to Peter Smith.
Thank you, Jim. Let me remind you of our mission goals. We came to the northern plains of Mars because the Odyssey spacecraft science team, led by Dr. Boynton, told us that there was water ice under the plains that at about 65 to 70 degrees northern latitude. So we wanted to find out about the ice. We're studying water. So within our mission right away, in the first couple of months of being on the surface, we were able to determine that the robotic arm could scrape through the surface soils only a few inches deep and reveal an ice layer. This is really important. And now our mission is about studying the history of this ice and soil that are within reach of the robotic arm, and to determine if this is a place on Mars that is habitable. Could Martian life live in this environment? And of course, we're somewhat biased when we talk about Martian life because we only know life as it exists on the Earth.
And so that's kind of the idea we have, is to see if this is an environment that Earth microbes could live in. And we're also studying the climate because we recognize that the ice at the surface is in close contact with the atmosphere, and as Jim has just pointed out, there is definitely a very close connection between ice under the surface and water vapor and ice crystals in the atmosphere. Let's take a look at our landscape in one of our latest panoramas. And this is the spacecraft in the foreground. And we'll take a little scan around to see just what this environment looks like. You see the solar panel in the middle of the frame there, and a mast sticking up that holds our temperature sensors and a little telltale by which we measure winds. There's a lot of things to see here. In particular, the ground is not flat like a parking lot, but it's kind of bumpy. And these bumps are typically 1 or 2 meters across, 3 to 6 feet across, and they're formed by the expansion and contraction of the ice. At least that's how it would be in the polar regions of the Earth. We have dug in the centers of the polygons and find that the ice layer is about 2 inches below the surface, and we've dug in the troughs and find it's as much as 3 to 5 times deeper in the troughs. So if you were to sweep away this thin soil layer on this what looks like a flat plane, you would find that it's really more like a skating rink. It's a very ice-rich environment. There's some things you don't see in these pictures, and that is large rocks, and you don't see dunes. So clearly there hasn't been a lot of material brought in by the winds to form dune fields and things of that nature. Nearby our landing site is a large crater, and we are actually on the material that was blown out of the crater when it was impacted some millions of years ago. And this is important. It's only a few million years ago that that crater was formed. It's a very new crater on Mars. It's not, the terrain we're on is not the thousands of millions of years old that is being explored by the 2 rovers, for instance. So we're looking at modern processes that are active on Mars today. This is a new environment that we're looking at, not an ancient environment. So what are the facts that we have on the table now after 3 months or 4 months of exploration of this landing site? We know that there's snow coming down from the sky. We see frost on the surface. We measure water vapor in the atmosphere. The atmosphere is a transport mechanism for water, ice, and for vapor. The vapor can actually permeate and diffuse through the soils and freeze out at the ice layer. And we know that the ice is just near the surface. We also know, as was just pointed out today, that we have calcium carbonate, which on the Earth would typically be in the form of limestone, and we have clay. These are indicators of a liquid water past. We know that it's an alkaline soil with a small sprinkling of salts, similar to the salts on Earth, and that there's a component of perchlorate. The perchlorate is actually a very interesting compound, and I'll get back to that. And we also know one other thing that we didn't learn ourselves, but have been studied by scientists over the last 20 years, and that is that the spin axis of Mars is not stable like on the Earth. It's now at 25.5 degrees, but over a few millions of years of time, it actually clocks back and forth, and at some points, it's actually pointed almost towards the sun. It can be tilted over at 60, 70 degrees tilt, and putting the polar region in a position where it's going to have a much warmer climate. So in the past, there's been a warmer climate. So how do we interpret all these facts? In this cold climate now, we don't expect that ice can melt into liquid water, at least unless it has a tremendous amount of salts in it. And so we don't expect to see liquid water at this time. But in the past, when the tilt was more and the climate warmer, we could have expected that this ice goes through a melt phase. And it doesn't mean it's a lake. It could just wet the soil a little bit. And is it that wetting of the soil that has created these carbonates and these clays that are now indicators of a past climate? And the nutrients that we see in the forms of salt, and the perchlorate, which on the Earth is a nutrient and a energy source for microbes. Is this a habitable zone on Mars? Well, I think we're approaching that hypothesis. We understand, though, that Mars has many surprises for us, and we have not finished our investigation. We have not finished our laboratory analysis or our data analysis, and so it's too soon to be sure of this. But we're certainly finding a lot of the indicators that we proposed to find early in the beginning of this mission, which is, to me, a great excitement. I mean, we never knew exactly what we'd find down here, and now we're finding indicators of a wetter climate and a nutrient-rich soil. But we haven't finished our investigation. We are not able to claim that we have found organics. We haven't looked at the key isotopic signatures of water that will tell us more about the history of the ice and compared it to the water vapor in the atmosphere. So this picture is still a little blurry. We're making good progress, but more lab work, more analysis is needed. And this is what we're going to be doing on our extended mission. And October is a very busy month for us so that we can complete our sampling and our analysis. And one other thing I'd like to leave you with is that we're also going to try something new in the last few weeks of our power-rich period of our mission. And that is, we brought a microphone with us, and this microphone was part of our descent imager. We had hoped to take sound bites, if you like, of the thrusters as we were landing on the surface. But this instrument now has been turned off. We weren't able to use it during the descent. It's been turned off for 4 months. We're not sure if it's going to work, but we're going to make a try. We're going to change the software on the spacecraft, and we're going to actually turn on this microphone and try and listen to Mars for the first time. So this may not succeed. It's a bit of a gamble, but we think it's worth it, and we're still trying these new things as we continue our mission. Dwayne?
Well, thank you, gentlemen. Incredible stuff, and I want to apologize to the scientists if I mispronounce 1 or 2 words on the experiment packages. So, okay, we're going to open it up for questions, and let's see. We'll start here. I'll go to the centers, and if you can wait for the mic and give your name and affiliation, please.
Dick Kerr from Science Magazine. Perhaps for Michael Hecht and Bill Boynton. I imagine you're reluctant to go here, but can you say anything more quantitative about how much clay, how much calcium carbonate you have? Is there any stratigraphy, layering to your detections? And if you like, wild speculation on how it got there.
Okay, why don't I go first, and then I'll pass things to Mike. In the case of TIGA, we don't have it fully quantified yet, but in terms of the carbonate, there's several percent, 3, 5, 6, 7, somewhere around in that area. It's not just a trace constituent. At this point, we still have enough I guess, analysis to go through. We've been working really so hard in trying to plan the experiments and do work around various things that the really detailed quantitative analysis hasn't come yet. So at this point, we're not clear if there's any variations as a function of depth. In the case of the clay minerals, if indeed that's what they are, in that case, it's a lot more difficult to talk about how much we have there, and for those at this point, I wouldn't want to hesitate a guess, but I'll turn things over to Mike.
There's not much I can add that Bill didn't say. We also see on the order of a few percent. It's difficult right now to put an upper limit on that, but I can tell you it's not, for example, much less than 8%. And as for where these clays came from, I think one of the great questions we need to ask is whether, in fact, this is just part of the blanket of dust that encircles the entire planet, or whether it's something local to the Phoenix site and the polar regions. We don't know yet, and as with TIGA, we still have a great deal of analysis to do.
Okay, we're now going to go out to JPL for a question from a media representative. You are Go Jet Propulsion Lab.
Hi, good morning. This is Raymond, a news reporter from China Press in Los Angeles. So a question to Peter Smith. So what's your comment about the China spacewalk or spacecraft at the last weekend? So also, do you think this is an opportunity for the further cooperation between China and the USA on space technology?
Yeah, let me jump in here, sir. That this is not the appropriate venue for that type of question. So if you can contact my office, we can get you the appropriate person to respond to that question. Let's now go to the Johnson Space Center for question.
Thank you. This is Mark Carreau from the Houston Chronicle, and I have two questions. The first one regards the search for the organics, and I'm not sure whether you sort of said that may be in the data, just not analyzed yet, or are you still actively searching with the different instruments, the oven and the wet lab? And my follow-up would be if you could say how many of the ovens and wet labs have not been used yet.
Okay. In terms of the ovens, right now we've used 4 out of the 8, so we still have 4 to go. We have done some looking for organic materials, and so far we can say if there's any there, it's not very much. There's some ambiguities involved. We also have this material called an organic-free blank that we need to analyze to make sure that any organics we might see are indeed above our blank level. So I think the best I can say right now is we are still looking. We don't have any definitive numbers on it that we can pass on.
Okay, we're going to now switch to our phone lines, and I would like to remind the reporters, if you can at all possible, direct your question to the appropriate person. We're having 2 sites here. We have a few second delay, so we want to make sure we can expedite that. So let's go to the phone lines. Ann Menard, National Geographic News. Go ahead, Ann.
Hi, thanks. I'm not exactly sure, let's see, who to... Perhaps Mike is the best person for this question, but the finding of calcium carbonate and possibly of the silicates, you made the comment that we have enough information to begin rewriting the book of Martian geochemistry. Could you expand on that a little bit? What did we think before, and what do these chemicals tell us now?
There were certainly suspicions of carbonates in the past. Similarly with the phyllosilicates, the perchlorate we discussed earlier, I think, was maybe 1 or 2 people had thought remotely about the possibility. But previous thinking was more in the line of magnesium sulfates. The sorts of minerals we've seen on the surface are in concentration with the rover missions, for example. So now what we have is minerals that are suggestive of past interaction with water on the one hand. On the other hand, perchlorate, which is very sensitive to water and would be dissolved in water, and that seems to be distributed everywhere in a way that doesn't suggest that we have large accumulations, at least in what we've seen with water. So what does this mean? Well, it means that we have a different chemistry in water that we had imagined, under which, for example, you might have a strong oxidation going on in certain circumstances. It means we have a very different situation in terms of pH, which controls everything from the opportunity for life, to how minerals interact with water in terms of erosion. So the chemistry is certainly different in terms of what controls the pH. It's different in terms of the chemical reactions that could take place, and it's different in terms of the nutrients that might be available to support microbial life.
Okay, we will now go to Andrea Thompson of Space.com.
Hi, yeah, I guess could be for Bill and for Mike Hecht. I was wondering, I know earlier this month it was mentioned that you guys were going to try and fill the rest of the TIGA ovens and then the remaining mecha cell. So I was wondering how that's progressing and when that might expect to be finished.
Okay, I'll take that. So far, we've still only got 4 filled. We've been working on some very difficult tries, I guess you see. We've gone back to try to get another pure ice sample or a very ice-rich sample. And you may remember we've had some problems in the past with the ice almost welding itself to the inside of the scoop. So we've been working through some difficulties. I think now we're still pretty optimistic we can fill all 4 before we run out of power, at least 3 to be sure. So I'm still pretty optimistic. We're going to get at least 3, if not all 4 of those ovens filled before we're done.
The situation with MECA is a bit different. We have successfully delivered soil to each of our 4 wet chemistry cells. However, one of them, the soil is in a pile on top of the funnel, and we didn't manage to get it into the cell. That was the one from a deep trough between the polygons. So what we have successfully done is taken a depth profile in the center of the polygons. We have not successfully sampled the region between it. We're looking at that. We're seeing if there's any way we can recover that cell and do something with it, but we may well run out of sunlight before we figure out how to do that. With our microscopy, we had 10 sets of substrates to work with. We will, if all goes well, within 24 hours have word of the final delivery. Now that includes 2 of the substrates that were set aside to collect samples just falling from the air. So we have gone through all those substrates. Again, if there's something else interesting to look at, we can find a substrate that's not too full of material to reuse. But we've certainly gone through the whole palette that we came to Mars intending to use.
Okay, we'll now take a question from Sally Rayo of the Planetary Report. Sally?
Can you hear me?
Yes, go ahead.
Hello?
Yes, we have you.
Hi. I think this is, thank you. This is for Barry. You had mentioned, I wasn't clear on this. Is it possible that you can resurrect Phoenix for more research after the Martian winter? Did I?
Well, it's theoretically possible. The vehicle is designed to have what we call a Lazarus mode, where after the vehicle loses all of its energy and the batteries are completely depleted, the sun will come up and actually recharge the vehicle after the long Martian winter. While that's theoretically possible, I don't believe that there's anybody on the engineering team that really feels that this will happen. No doubt in the probably October timeframe of 2009 we may go listen, but I don't think it's very likely. There are too many things working against us in that regard. The temperatures are going to drop. Jim had showed the curve of how low the temperature is getting now. It's going to get a lot colder pretty soon, and then we're going to lose the sun for 3 months straight and then have very little for quite some time. We're going to face a couple of problems as the ice builds up on the solar rays. We may be seeing the solar rays crack, if not fall off. We're going to go through what we call a glassification temperature, where the material around the circuit boards gets so brittle that they turn into a glass-like material and actually crack. And for those of you who've dropped your cell phones, you'll know what I mean. When printed wire boards crack, the instruments don't work very well. So it's very unlikely it's going to work, but we'll sure give it a try.
And we will now take a question from David Perlman from the San Francisco Chronicle. Go ahead, David.
Yeah, hi, people. Thanks very much. Thanks very much. I hope you can hear me. I just have one quick question following up on Barry's comments about the resurrection, and then I'd like to ask Peter a question quickly. On Barry, could you give us the maximum and minimum temperatures that were on that chart? I cannot read them on a TV here, and maybe other folks are having the same difficulty. And then for Peter, I would like to know the significance of the perchlorates other than as an energy source for potential microbial life.
Okay, well, I think you were referring to the hours of daylight. There were no temperatures on that chart, so what that chart was really showing is the number of hours or minutes per sol that the sun was above the horizon illuminating or potentially illuminating the solar arrays. With regard to what the temperature extremes might be, I would defer that question to Peter or to Jim or somebody who knows better about the expected temperatures in the wintertime.
Answer that, Jim.
Okay. So around the time of the winter solstice, when Phoenix definitely won't be operating and will be covered in CO2 ice, the temperature will be well below negative 120 degrees Celsius, negative 150.
Okay, I can answer the question about perchlorate. Perchlorate is quite an interesting subject. There's quite a lot of literature about it in the chemistry literature. It's, of course, used for an oxidizer on solid rockets. The space shuttle uses, I think, ammonium perchlorate in its solid rocket boosters. So perchlorate is used quite a lot in industry. It's also in known if you mix perchlorate with water and then freeze it, you can lower the freezing point of water down to temperatures as low as -60, -70 centigrade. So that leaves some interesting questions in your mind. If water did flow in places on Mars that have even small amounts of perchlorate, it might get concentrated in low areas where it might pool together. And if that were to be the case, then you could certainly form brines. Now, whether we have brines at our landing site is a matter of discussion, but we have not seen them with our robotic arm and the cameras on the spacecraft. So let's see. Other properties, it's useful to microbes. Microbes use it for an energy source, and I think there's a whole lot of other chemistry that I'm not very much aware of. So it's a very interesting material to find on Mars, and I'm sure there'll be lots of intense research into what it might mean to Martian science.
We'll now take a question from Alan Fisher from the Tucson Citizen. Go ahead, Alan.
This is for Dr. Boynton, please. Dr. Boynton, you mentioned earlier that there are 4 ovens left and that you've had some difficulty getting the ice material into the ovens. Is that an issue of the ice getting stuck in the scoop or the ice getting stuck on the screen? And as a follow-up to that, is getting the icy material analyzed still the highest priority remaining for the TIGA instruments that are, or for the TIGA ovens that are left?
Okay. Until recently, the most difficult part of this problem was getting the icy soil out of the scoop itself. Originally, even before that, it was figuring out how to collect the stuff and rasp it and go through all of those difficulties. We had one attempt at delivery where the alignment was actually off and we missed the target and didn't actually get it onto the screen. Finally, just a few days ago, we did get some onto the screen, but it didn't go into the oven. We interpreted this as the soil, again, being very clumpy, and just some property of it makes it so it doesn't easily go into our ovens. And what we're doing now is we're, at least from this particular location, we're not going to try to get that very difficult ice anymore, just with the idea that it's very, well, it's a hard thing to do and we're kind of running out of time. We're still keeping open the option of trying in another area called a cupboard where we also see ice, and maybe it's ice of a little different kind. So that's still on our list of things we want to try in the future.
Okay, next up is Rachel Cortland from New Scientist.
Yeah, hi. I guess this is a question for Bill or Mike. I'm still a little unclear as to how this changes your sense of the geochemistry of Mars. In particular, do you think there was, as the poles of Mars moved, was there flowing water or standing water, ice that's sublimated and created a giant puddle? Or, I mean, can you build up some sort of picture of what you think might have created these carbonates?
Okay, I'll begin and then pass it over to Mike, since he was making the more general comments, I guess, about the geochemistry. One of the things that does look different, at least to me, about the carbonates here is, as I mentioned, we're not in an area where we had flowing water. At least there's no evidence of it. Doesn't mean it wasn't flowing there at some time. And assuming that we really do need liquid water to form these carbonates, which appears to be the case, then what this says is we might have had standing water some point in the past. It's possible that the ice that there is melted in situ and it stayed right in that spot, and the reactions happened there. It's really kind of all up in the air, and it's a little bit hard right now to say exactly how this might have happened and what the constraints are. And these are some of the things that, when Doug was referring to the data that's going to keep scientists occupied well into the future, this is clearly, I think, one of the questions we'll be trying to come to grips with over the next several years. But I'll pass it on to Mike for his comments.
Not much to add to Bill's comments about the carbonates, but I'll comment on his remark that it's all up in the air. The perchlorates, again, which change much about the chemistry as well as the behavior of water in the soils as they absorb the water and really keep the soil around them dry. The carbonates are formed up in, the perchlorate and that family of oxidants are formed up in the air, as they are on Earth. It's a result of photochemistry, materials that are formed with the assistance of sunlight, with the assistance of droplets of water, and they fall to the ground and mix in with the soil. So understanding the way the atmosphere and energetic processes in the atmosphere affect the soil and the way the soil interacts with the ice underneath it is a very, very interesting subject, and we really didn't expect it to go down that pathway with perchlorates. We've talked about oxidants on Mars, things like peroxide, for years. This suggests that there's really a different family and a different set of pathways that have to do with highly oxidized species, which we don't see so much on Earth, falling from the skies and interacting with the soil. So that's yet another chapter in the book.
And Ken Kramer from Spaceflight Magazine, you're up next on Phoenix Call.
Hi, thank you. Well, first, congratulations on a great mission. I have a question for Barry Goldstein. I'd like to know if you're going to use MRO to photograph Phoenix at all, perhaps one image or a series of images as the carbon dioxide ice is being built up, and when you might do that. And also like to know from Peter, you've moved to headless rock. What have you learned, or what do you hope to learn? Thank you.
Well, we've obviously talked about that. It hasn't been formalized, but I'm sure that our request to do that will be honored. We still have some months to go before we start being encased in the CO2, but we have discussed that around the program office, and I'm sure it's going to be finalized. A lot of the details of when those images are taken have to do with the orbit of MRO and when it's in the viewing site. So I'm sure we'll get those done over the course of the many months that we're basically frozen on the surface.
I can take the second part. We moved the rock called Headless about 40 centimeters, and the purpose of that was to see, of course, what was under it. Now, if a lot of these materials are falling down from the sky onto the surface, they aren't likely to be falling under a rock, so there might be some differences just from the airfall material. And also, if there's any small films of water that are created in the warmer periods of Mars history, they tend to stick to the surfaces of rocks and produce salts. So we're hoping to find a different chemistry under the rock than next to the rock. So the rock has been moved. We see subtle color differences in the soil directly under the rock as compared to the soil around it, and we're quite anxious to take a look at this in some of our instruments. So hopefully in the next week or so we can get a sample into one of our instruments or several of our instruments, and then we want to look at the ice table under the rock to see if the rock warms more than the soil and actually depresses the ice table in response. And this has been modeled by one of our scientists, Mike Mellon at the University of Colorado, and he's really anxious to see if he can test out his theories on an actual Mars environment.
Okay, we normally limit these briefings to an hour, but we still have several questions on the line, so we're going to keep the lines open if you gentlemen don't mind and take some more questions. And next in the queue is Raphael Jaffe from Aerotech News.
Yes, my question is for Dr. Smith or the gentleman who's handling the Dr. Hecht. The soil layer is dry according to the probes that were stuck into it. However, there is definitely ice below it. How can that work?
Mike, do you want to take that?
Start, and then we can...
Okay, how can it work that the soil is dry above ice? Well, the temperatures change as you go below the surface, and ice is stable once it reaches, or at least the water vapor can freeze once it gets to the point where the temperature is the right value. And at this time of year, that's several inches below the surface. As you move above that, the temperatures are too warm for the ice to form, and it tends to be very dry. Now, the dryness of this soil is quite a mystery here, and we wonder if perhaps the perchlorate is also absorbing some of the water. And Mike, you've been studying the perchlorate. What do you think?
With a little bit of a technical glitch, I didn't hear all of your answer, Peter. But certainly the perchlorate is likely to play a role in how dry the soil is. Water vapor will come off the ice, for example. The perchlorate will tend to suck it up. It's a desiccant. And we are thinking that may well be part of the picture. We say dry, not because there isn't ice there, not because there isn't H2O, but because there isn't anything in the form of even very thin films of liquid water that might exist at cold temperatures and mixed with salts. So when we landed, we didn't know whether we'd find different types of liquid or just dry soil and ice underneath it. And right now it seems like it's dry soil and ice underneath it.
Thanks, Mike. Now, next in the queue is Ann Menard with National Geo News. Ann?
Hi, thank you. This is another question sort of about the new news. There have been a couple of studies coming out lately that are finding evidence for a wet Mars either in the first billion years of its history or even in the billion years after that. For Bill or Mike, do you have any idea of the timing of the wet interactions that would have formed the carbonates and the possible silicates? And then Peter referenced a possible melt phase. Could the melt phase have coincided with that or been another opportunity for a wet Mars and for life to form?
Okay, I'll begin with that. From my standpoint, I don't think I could really hazard a guess on when this might have happened. This is the kind of thing that might actually have to wait for some time in the future when we actually bring samples back from Mars and can date them and things like that. But I don't know, Mike, if you want to add anything to that.
Really, no, nothing I could add to that.
Okay, let's go back to Sally Rail, Planetary. Sally, are you with us?
Hi, thank you. I just wondered if you could go through a checklist of what needs to be done still for mission success. To Doug or Peter?
Well, we wrote in our proposal that we would attempt to measure organic materials in the soil, and part of that measurement is to get our organic free blank that we brought with us from Earth. That sets the zero line, if you like, as to where terrestrial organic contamination exists on the spacecraft. And then if we measure a considerable amount above that in some of our cells, in some of our ovens, I mean, then we can start to talk about Martian organics. Now, Martian organics don't necessarily mean these are biological systems. Could well be that the organics were brought by comets or asteroids to the surface of Mars and preserved in the ice. So we have that yet to do. We haven't measured the blank, and we haven't compared it with the measurements of our cells. So that is one thing. And the other is we're really interested in the isotopic ratios of the water vapor and the water ice. So comparing the deuterium to hydrogen ratios in the soil, and in the ice in the soil and into the atmosphere are going to tell us if these systems are working together. We have a reservoir of water vapor, a reservoir of ice. Are they really interacting, or is there some of this ice perhaps from an ancient time or another time from the past, and therefore out of balance? So those two things come to mind quickly as something we want to do. And finally, completing our climate and weather observations, our study of the atmosphere throughout the entire length of the mission is a prime goal. So those things are left.
Do you want to add anything to that?
The only thing I'd like to add is that NASA sets specific mission success criteria in what's called the Level 1 requirements. It sounds rather technical, but the point is when we design a mission or go out and have someone fly a mission for us, we define what we want out of that mission through those documents. The Phoenix mission actually accomplished all of its full mission success criteria in late August, so they're completely done and meeting all the Level 1 requirements in that regard. So this is extended mission. This is great new science, great addition to the basic mission that NASA was looking for at the beginning, and so this is where these guys are headed. Good news.
Thank you, Doug. And I believe we're going to go back to the Johnson Space Center for a question.
Thanks. It's Mark Carreau from the Houston Chronicle, and I had two questions. I'm wondering if you can kind of dial back to the start of the briefing and estimate how long you think Phoenix can last electrically into this extension that you've approved. Is it a matter of a few weeks, or is it maybe past the end of October? I just wondered if you could sharpen the estimate a little bit.
Peter, did you want to start, or you want to send that out to Barry?
I think that's a Barry question.
I think I'll handle that here in Pasadena. We have been modeling both the consumption of energy as well as the production of energy, and we actually have been correlating and basically verifying those models are correct by measuring how much energy the vehicle produces every sol. And basically what we see is we see a downward sloping curve, as you would expect, with the sun going down below the horizon for longer and longer per sol. And based on those estimates and based on those predictions we have, it looks like we meet the point where the production needs crosses the, I should say the consumption needs crosses the production curve, looks like somewhere at the end of November. The accuracy of that is obviously a little bit fuzzy as you go on. Every sol it varies a little bit. But we feel confident that the vehicle will survive all the way through the mid to latter part of November. Now, given the fact that we err on the side of conservatism many times, it's quite probable that we'll last beyond that point. Now, whether we'll last beyond that point a couple of days or a couple of weeks are the issue in question. It's not as though the vehicle is going to survive a number of months past the end of November. So right now we put together a plan to operate the vehicle as a weather station in the months of November and December. I find it very unlikely, considering our models are being validated every sol, that we will have enough energy to go beyond that point.
Do you have a follow-up?
Boynton. Yes, one more question for Dr. Boynton, I think. I guess I wanted to understand what your best chance now is to see organics if they're there. Is it through the use of the remaining TIGA ovens, and is that in fact, I just want to make sure I understand that's what you hope to do with the ovens is to search hard for that if it's there?
Yes, we will be looking hard for the organics, and it's one of the things for all of the remaining samples that we're going to be putting in there. We will be looking for the organics and analyzing for those masses in the evolved gas analyzer. So we are going to give it our best shot in every one of the future samples we do.
Okay, folks, we are going to bring it to a close here. I want to thank our participants. We will be replaying the visuals that were presented during the presentations. Of course, you can go to www.nasa.gov/Phoenix for the latest developments. And on a programming note, there are some developments with the Hubble resurfacing mission. There will be a media telecon at 6 p.m. Eastern today. Call your respective NASA Center newsroom or headquarters newsroom at 202-358-1600 for details, or go to the website. Again, congratulations to the Phoenix team. It has certainly been an exciting time, and science never sleeps, and science is definitely very active today. Thanks for joining us.